Okay, should we get started? Okay, I'll try to move quickly because it's a lot of information, but I want to make sure that there's time for discussion and feedback and questions. Okay, so starting off with some context. Uh, the on-sky commissioning with LSST-CAM is progressing well, but we're not done, right? We're right in the throes of it at the moment, and we're looking ahead. And if you see these weekly commissioning updates, you'll kind of get a sense as to where we stand. But over the next month, what we're looking towards is a gradual transition from primarily engineering activities to a period where we have more sustained observations and we're continuing the optimization in parallel. So the pilot observations for the SV surveys, we're talking about a few hours per night, could begin as early as, say, 2 weeks from now in mid-June and would continue through September. There's also like another piece of context in terms of the timing is that there's a planned downtime for several weeks in September, October for remaining system integration work and maintenance. And so there's sort of a natural pause here. So the science validation surveys, just to remind people of what these are, as part of the construction completeness and operations readiness criteria, there's a number of specific items to demonstrate. And one of those is to conduct autonomously driven SV surveys. This is the final stage of the on-sky commissioning activities during construction. These are intended to be a full rehearsal of the science operations. That's the 24-hour cycle at the summit, as well as the survey scale data production of both prompt processing and data release processing. These are intended to be a minimum 30-day span, so it's about 1% of the 10-year LSST, and it would incorporate procedures over a full lunar cycle. So the document that describes those construction completeness and readiness, operations readiness criteria, SITCOM TN 005, has a description of this baseline, and that's fleshed out a little bit more in the early science program document RTN 11. We're at the stage now where we've taken that concept and we've developed a specific instantiation of a scheduler configuration for those SV surveys that's informed by the specific fields that are visible right now in the current progress of commissioning. And we believe that if this were implemented, that we'd be able to meet the construction completeness criteria. So there's a couple connections here that are useful, and we've already touched on those a little bit in our discussion. One is that the SV survey data, in addition to the construction completeness, will also hopefully serve as a basis for several components of the early science program. So for one, all of the science grade data collected during on-sky commissioning is expected to be reprocessed and put into data preview 2. Second, once we have shown technical readiness to produce the public alert stream, and that's been approved, we hope to use the SV surveys to start building up some template coverage and running difference image analysis and producing alerts, though with some latency and a lower volume while that is being commissioned. And then there's also the template generation looking ahead. If we're able to execute the survey as designed, we would cover something like 10% of the LSST footprint by the end of the on-sky commissioning period, and that would be available, hopefully, for difference image analysis during LSST year 1. So the other piece of context is that we've already been taking some observations that could be useful for the science community. Some of these are for the Rubin First Light technical milestone, and others have been for the First Look celebration. So as one example, we now have full 6-band UGRIZY observations of the Cosmos LSST deep drilling field, as well as some observations of a densely dithered star field near the galactic plane. In general, because of the way that these observations had to be taken, they actually have a much denser temporal sampling than is typical of the LSST or LSST nominal cadence. And they also tend to have deeper integrated exposure than what would be acquired during year 1. So these are interesting complementary data sets. Another aspect of this is that we're going to continue doing these types of observations for probably the next month as we're starting to fold in the pilot observations for the SV surveys in parallel. In terms of the boundary conditions, we are at the stage now where we're going from the concept to the concrete instantiation. So we have more information about the progress of the on-sky commissioning. we have more information about the plans for Rubin Observatory operations. And so as an integrated project, we're thinking about, how do we optimize all these different pieces? That being said, there's this boundary condition that the SV surveys are a construction deliverable. And if pressed, then the construction team might need to prioritize the remaining on-sky time specifically to advance the construction closeout objectives. But where we have flexibility, we'll try to, hopefully you'll see that we're making designs that advance all of these objectives. In terms of input from the Rubin science community, this has been an important part of our thinking. So in 2020 and 2021, multiple science collaborations submitted commissioning notes that described science validation activities. Thank you very much for that input. That's been on our mind for the past several years. We've discussed plans regularly at the RCW workshops and other sessions, and including discussions of the early science program. Also, we've been paying close attention to the development of the LSST cadence that's been facilitated by the SCOC. So all of that's being folded in here. So next steps. So what we're doing today is that we are sharing an SV survey design recommendation along with example simulations to show what the coverage could be if we were to begin the pilot observations in mid-June and then have a relatively high level of operational efficiency sustained for 2.5 months, beginning in early July. Those plans could be updated. We are still in the process of commissioning. We're still understanding the system capabilities. So we have to be responsive to that. The final design will be approved by the project director, Željko. And with the pilot observations beginning as early as mid-June, we're basically going through the process of implementation now, and then the design will need to be finalized probably by early July. If we continue at the current pace. So as mentioned earlier, basically following the discussion today, you have the slides, but we're going to try to put the information into another document, probably RTN 11, so that information is broadly available. Okay, so let's go to the design recommendations themselves. So the baseline SV survey design concept that we've been talking about for several years now has these basically two interleaved components, a deep component that was intended to be something like 100 square degrees with the full band coverage to 10-year LSST wide fast deep equivalent depth. And this was primarily for testing coads at the nominal LSST 10-year depth, but it also would provide a deep, basically a higher temporal sampling as well, just to get all of those exposures in a finite period. In addition, there's a wide component envisioned to be on the order of 1,000 square degrees, potentially in fewer bands, trying to get to at least 1-year LSST wide fast deep equivalent depth. And this was optimized for testing alerts at survey scale. So we took that baseline concept, and what we've done is that we've recognized that there's an opportunity that we can advance all of the goals of construction closeout, operations readiness, and the early science program if we take that concept and we incorporate aspects of the standard LSST cadence. I'll talk about what that means in a moment. But we still will need some modifications so that we get a self-contained data set for science pipelines commissioning, the science validation, and the early science program in the finite period that we have for on-sky commissioning. And then where flexibility exists, we're going to try to make choices that have the widest opportunities for science validation across the primary science drivers. Okay, so here's what we mean by, what do we gain by incorporating aspects of the standard LSST cadence? So we think that this has benefits to construction completeness because it basically gives us a little bit more flexibility in terms of the scheduling when we have a broader, basically RA distribution of targets. It also simplifies our verification validation because we're collecting data that is directly representative of the LSST survey. From an operations readiness perspective, this gives us a chance to directly validate the standard LSST survey implementation, we can make some informed decisions before the start of operations. You can think about it as a risk mitigation because we're already exercising something similar. It allows the team to focus on increasing the operational efficiency, and it means that it moves us closer to having a seamless transition from construction to operations. In terms of the early science program, there's several advantages. One is that it gives data management, basically from a algorithms development and infrastructure standpoint, data that's representative of the first year of LSST. It gives the science community data products that resemble LSST sooner so that there's more opportunities to provide actionable feedback. It gives us opportunities to provide template coverage, and it gives us some level of flexibility in terms of defining coherent data sets. And then to kind of synthesize what we have learned from the science community in terms of all the input that's been received, what we were trying to do was to include basically as many of the different science cases as we could. So we want to have coverage of the galactic plane. We'd like to have deep multiband coverage of the LSST deep drilling fields. We want to have some higher cadence temporal sampling than the standard LSST wide, fast, deep survey to help validate various time domain science cases. We want to have wide area template coverage as possible within these constraints to accelerate the time domain science opportunities. And that includes coverage of the ecliptic region to support solar system science validation. And in general, we want to have multi-band observations to support the broadest range of science validation studies as possible. So with that in mind, one of the aspects that we were looking at was the visibility of the LSST deep drilling fields, as those would be sort of anchors for thinking about how to do the design. It turns out that if you look in early July, Cosmos is set for the season, and there's one of the LSST deep drilling fields in the South Galactic Cap that is visible, and then the other three become visible by the time we get into early September. For a couple hours a night. And so if we are planning this period that extends through mid-September or so, then we expect that we will be able to get some coverage of the LSST deep drilling fields. So we took all of this input and we started developing a simulation. And this chart here is showing our assumptions, at least for the purpose of generating this design and the simulations, what we were thinking about in terms of the operational efficiency. So the concept is that starting in mid-June, we'd spend something like 2 hours per night in dark time for pilot observations. This is basically to exercise from a technical level that we can execute the survey, we can identify problems early, we start giving data management representative data to look at. We give the operation, basically the summit observing team, opportunities to go through all the workflows. So we start with those pilot observations, and then starting in early July, we would go to what we're hoping for is something like 75% efficiency. We have achieved this level of efficiency on multiple nights so far, but there's still more work to do over the next month to actually realize that efficiency sustained over multi-month periods. So this is what we're working towards. One constraint is that there's no SV survey during the last hour of the night. So that's the hatched out region here that's devoted to other engineering tests. Right now, in terms of the visit, we are working with single 30-second visit exposures in GRI, Z, and Y, and then a single 38-second exposure in U. And there's no near sun twilight NEO survey for this simulation. Some caveats. So the recommended SV survey design, it represents our target. It represents our goal. We're basically working towards the LSST system specifications, and we have to be prepared for success. And that's what this design represents. It's important to note that we are still in the commissioning phase, and a central objective of the SV surveys is to directly test and to optimize our operational efficiency under realistic conditions. So we're basically using these months to try to improve our performance. It could be that the volume of science grade data that's actually realized could be impacted by the current uncertainty in the system level performance, weather in the Chilean winter, and so forth. And what that means is that the actual volume of delivered science grade data from the SV surveys might be a fraction of the design that you're going to see in the next slides. If the realized operational efficiency during the pilot observations in the next weeks is lower than expected, then the current thinking is that we would try to reduce the footprint area by a corresponding amount. That would ensure that we're able to get to the integrated exposure and the number of visits and be able to generate templates. So we would still try to include all of the components of the SV survey, but we would just downsize the area. That's the current thinking. Okay, so with all that, let's talk about the detailed design. So the so-called enhanced SV survey design candidate consists of a deep component, which would be the LSST deep drilling fields themselves, implemented in a mode similar to what we would expect during year one of LSST. Those would be observed in UGRIZY. It's a total of 60 square degrees if you include all of the South Galactic Cap DDFs, plus the Cosmos observations that we already have taken. And then that would be complemented by a wide component that would be implemented effectively as LSST year one, wide, fast, deep in all 6 bands, but constrained to a region around the ecliptic, for example, plus or minus about 10 degrees. And that's to ensure that we build up template coverage quickly enough that we can start testing alert production at survey scale during the time period of the SV surveys themselves. That's what you see here as this extended region here, and it has this shape because it's following the ecliptic. So looking a bit more closely at the expected number of visits per band, so if we were to execute this, again, with the desired or with the target efficiency, it'd be a total number of visits that would be comparable to LSST year one, wide, fast, deep in the low dust region. And you'd see that this is covered in all 6 bands. In terms of how quickly we're able to build up the template coverage, so initially there's this pilot period where we're observing at something like a few hours per night. And then once we start increasing the duty cycle, we'd start building up template coverage relatively quickly. So within the first 20 days or so, you'd start having coverage over several hundred up to maybe 1,000 square degrees. And then the idea is that we would start the incremental template generation to exercise that component of the whole data production system and then increase our capability to test alerts throughout the period. The goal is that by the end, we would have several thousand square degrees of coverage where we're producing alerts. For the LSST deep drilling fields, this is a chart that shows, again, this is MJD on the horizontal axis, each of the fields, showing the temporal sampling. And on the right is the total number of visits that we expect to be acquired. So it turns out that the Elias field, this is the one that becomes visible by early July. And so that starts getting observations sooner. Euclid Deep Field South doesn't become visible until closer to late August, September. But the idea is that we try to get consistent temporal sampling throughout the SV survey period, and the total integrated depth in terms of the number of visits would end up being comparable to the 10-year LSST wide, fast, deep. Elias would get a little bit deeper just because it becomes visible sooner. But in general, the goal would be that the coverage would be similar to the target that we had considered in the baseline design. I'd like to show just a few possible variations just to give a sense of where we're still thinking about the detailed optimization. So one possible variant is that we could, for example, remove the constraint on right ascension so that we would effectively wrap around the full sky if we were to continue for a full year. So that has the effect here where, rather than rather than a region that extends basically from one end of the galactic plane to the other. It could go a little bit further. We've also talked about in the north ecliptic spur, in the nominal LSST cadence, this is only covered in G, R, I, and Z. And so we could imagine limiting the band coverage in this region specifically. When we do these types of variations, the coverage in the LSST deep drilling field is largely unchanged. So this is what that could look like. This is a variation. So again, on the north ecliptic spur, no U band, no Y band, potentially wider coverage on this end of the footprint. However, when you do this, you get a smaller number for the median visits per band. And so we have some hesitancy for this kind of design, because if the efficiency is somewhat lower, there's a risk that we might not be able to achieve the template coverage for testing difference image analysis as early as we otherwise would. And this is the primary reason why we recommend this design, because the more constrained footprint gives us a higher probability of being able to test that alert production at scale, and it still gives us good coverage of the galactic plane on both sides, so that we try to cover as many science cases as possible. This is what that area with possible template coverage could look like in this variant. Again, you see that the total template coverage is a little bit larger, but not necessarily dramatically so, maybe 20 or 30%. So in terms of the types of variations that we're trying to optimize around right now, an example is what we were just talking about, whether there's a constraint on the right ascension range of the wide component. Do we have full band coverage in the north ecliptic spur, or GRIZ only? Do we have uniform coverage across that stripe along the ecliptic, or do we have a somewhat lower visits in the dusty galactic plane? For the deep component, we're still thinking about the exact details of, do we have fewer nights with longer sequences or more nights with shorter sequences? Is there any optimization that we want to do around the dither pattern? I know that there's a group that's been actively thinking about this. Our goal would be to try to adopt something that is useful and informative looking ahead to the LSST survey, if that's possible. And then in general, there's a question of the balance between the wide and the deep components. However, I'll just note that this recommended design, by construction, achieves this target of reaching the 10-year LSST wide, fast, deep depth in the deep drilling fields, while also getting this 1-year coverage in the wide region. And so there's probably not too much flexibility if we're trying to achieve both of those goals, but putting that out for discussion. I'll just close by very quickly mentioning some alternative SV survey designs that we considered, but are ultimately not recommending. So one of the ideas that we looked at seriously was literally just starting the standard LSST year 1 cadence. So basically take the recommended design and just roll straight in, including the deep drilling fields. However, we found that if you were to look at simulations of what this would look like over the roughly 3-month period of the SV surveys, the typical expected number of visits per band overlapping is something like 3 to 5 visits. And what that means is that there's a minimal margin for template generation. And if the SV survey period were abbreviated or the realized efficiency was lower than the nominal LSST, there's a significant risk that we wouldn't be able to actually build effective templates. This is graphically that same concept, but just shown so you can see what it looks like. This is if you did 3 months with the standard LSST cadence. This is actually for a different start date, but it gives you a sense of what the issue is. What you can see is that you get much wider coverage, but the number of visits is, again, kind of this 3 to 5 range, and it just gives us very little margin for testing the templates if the efficiency is lower than what we expect. So we're not recommending this design. We also considered designs with a single contiguous area at high galactic latitude for the deep components. However, there are some constraints based on the actual time of year. It turns out that we are coming into the time of year where the galactic plane is right overhead. And so that limits where you could put this deep component. We also understood from the science community that having multiple LSST deep drilling fields would provide more opportunities for comparisons with external reference data sets. It gives you more targets at a range of visibility throughout the year. It's hopefully more useful in terms of having template coverage going into the first year of LSST. And it gives more opportunities for scientifically validating photometric redshifts by having that broader coverage. And so, for example, we looked at designs like this. This is kind of an early concept of what that could look like, but we felt that the recommended design was better because it offers more scheduling flexibility. It achieves better coverage of the galactic plane. It achieves more coverage of the ecliptic fields. And so, again, what we were leaning towards is something that looks more like this to try to cover as broad as science cases as possible. Okay, that's it.